Hi everyone, my name is Ana Serrano, and together with Daniel Martin, we will present our work Imperceptible Manipulation of Lateral Camera Motion for Improved Virtual Reality Applications, which was carried out at Universidad de Zaragoza in collaboration with the Max Planck Institute for Informatics. So let's start with some motivation to see why we are interested in this. Virtual reality systems increase immersion by reproducing users' movements in the real world. However, several works have shown that this real-to-virtual mapping does not need to be precise in order to convey a realistic experience. This has been leveraged, for example, in the context of locomotion, leading to significant results in redirected walking to enable the exploration of virtual worlds larger than the available physical space. However, locomotion is not always possible. In many VR applications, the user is seated or standing with only head and upper body motion available. This is the case of scenarios and games that involve long-term use of VR systems or simply due to limited space. For example, home setups do usually suffer from severe constraints in physical space. According to the Steam Hardware and Software Survey, only 1% of Steam VR users use a play area larger than 3 meters by 3 meters. Game designers are aware of this limitation. None of the top 10 VR games in 2019 use forward locomotion. Instead, these games offer teleportation or camera displacements through controllers for larger distances and rely on the user's limited motion only for local camera manipulation. In the absence of locomotion, lateral translation becomes very relevant. It is a natural motion and it is used very frequently for many actions such as dodging. It also facilitates scene understanding by triggering motion parallax, which is one of the strongest depth perception cues. To cover these scenarios, we investigate how much we can compress or expand the user's lateral motion while these manipulations remain undetected. With this, we derive detection thresholds for the manipulation of lateral camera motion in response to the corresponding head motion in virtual reality. We also show how our findings can be applied to 3 key open problems in VR: improving 6 degrees of freedom viewing of captured content, overcoming physical space constraints, and reducing simulator sickness. To our knowledge, we are the first to investigate the range of imperceptible translation gains for lateral camera motion in response to the corresponding natural head motion. In particular, we have focused on upper body motion in the absence of locomotion. Further, we have discovered for the first time that these detection thresholds are influenced by the depth layout of the scene. So let's see how we measure these thresholds. We devised an experiment in which participants were placed in a virtual environment showing a large square room with some furniture to provide some natural motion parallax cues and depth discontinuities. For simplicity, here we show only a schematic in which we depict one of the walls of this room, which is set to a fixed distance of 6 meters. Surrounding the participant, 3 planes appeared randomly in 3 out of 4 predefined locations between the user and the wall. These planes are set at a certain distance to the user, which will vary during our experiment. Behind of these planes, there was a hidden coin, and the participant's task was to find this coin. In order to do so, we asked participants to perform left-right movements with their head and upper body while sitting on a stool, and we applied to this movement a certain translation gain. We define a translation gain as the mapping between the real head translation and the virtual camera translation. Then, values lower than 1 indicate a compression of the real motion, while values greater than 1 indicate an expansion. The reason why we introduce this search task is to naturally prompt some head motion while inducing fixations on a depth edge in a natural scenario. This is a key aspect of our methodology, motivated by fundamental research in vision science showing that measured thresholds are significantly different when the user is interacting naturally with the environment compared to rigidly controlled viewing setups. We sampled 7 values for translation gains, including both compressions and expansions of the real movement. We also sampled 5 different plane distances with the goal of analyzing if the depth layout of the scene may have an impact on these detection thresholds. Each participant sees each of these conditions 5 times. This yields 175 trials that each participant has to complete. And the question we ask them after each trial is this: has your virtual movement been larger or smaller than your real head movement? We recruited 30 participants for a study, which means that each condition is actually seen 150 times. Once we have all these measurements, let's see how we compute our detection thresholds. In this plot here, we have in the x-axis the 7 translation gains we have sampled. Then in the y-axis, we're going to plot the probability of answering that the virtual movement was larger than the real movement. So a probability of 1 means that the movement was always perceived as larger, while a probability of 0 means that the movement was always perceived as smaller. For each translation gain and for each plane distance, we average our 150 answers. For now, I'm just showing here the average answers for a plane distance of 2.5 meters. And the error bars represent the standard error of the mean. Finally, we can fit a psychometric function to our data, which looks like this. This function has 3 important features. The expansion threshold, which is the translation gain corresponding to a 75% probability of correctly answering that the virtual movement is larger. The compression threshold, which is the translation gain corresponding to a 25% of this probability, or in other words, a 75% probability of correctly answering that the virtual movement was smaller. After these 2 definitions, the gray area indicates the range in between these thresholds in which manipulations will remain undetected. Finally, the translation gain value at which the participants responded at chance level is termed the point of subjective equality. At this point, participants perceive their head motion and the camera motion movements as identical. So a point of subjective equality equal to 1 would indicate that users perceive translations as perfectly identical in real and virtual spaces. But interestingly, this is rarely the case. The bias we are observing here can be also found in different VR scenarios, and it's usually indicative of underestimation or overestimation of virtual translations. Now, we can do the same for all our different plane distances, and this is how it looks. One very interesting thing that we found is that points of subjective equality increasingly shift towards larger translation gains as the plane distance increases, affecting the corresponding detection thresholds. So there is actually a dependency of the thresholds with the depth of the observed plane. Later, we will take this dependency into account for our applications. Finally, we have used all the head tracking data collected to perform an analysis of participants' behavior, so if you're interested, please refer to the paper. Now, Daniel will take over to explain how we leverage our thresholds for different applications.
As we have mentioned, our thresholds have been computed in free viewing conditions, and so we can apply them to different applications. Therefore, we have evaluated their applicability in 3 different key problems in VR for which no definitive solution exists yet, to verify the improvement yielded by our technique. The first application is devoted to bring an improvement in terms of visual quality to 6 degrees of freedom viewing systems. Our second application shows how our method can help overcome physical constraints during VR experiences. And the third one is a proof-of-concept application to test whether our thresholds can be used to reduce motion sickness. We will start with our 6D viewing application. Common 360 footage is usually captured from a single viewpoint. Thus, the only information available is what the camera could capture from that fixed position, and there is no information about any occluded areas. Therefore, this footage lacks motion parallax, which is unnatural and can induce discomfort and heavily degrade the experience. Previous works have already shown that users prefer SIGGRAPH interaction and navigation, and due to that, some works have been devoted to enable SIGGRAPH viewing in 3D content, providing the necessary motion parallax to ensure realism. However, this kind of works result in some artifacts in the disoccluded areas, as there are in-painted areas of the scene that have not been captured. As the user displacement increases, these artifacts become more and more visible, degrading the final experience. To alleviate this, we propose to use our compression thresholds to reduce the virtual camera motion, hence reducing users' displacement and therefore reducing artifacts' visibility. When applying our thresholds to complex scenes with varied depth layout, and in order to consider the dynamic behavior of the viewer, we resort to a parameterization of our thresholds based on retinal velocity. Please refer to the paper for details on how this is done. With this information, we get a map that yields how much compression can be safely applied in each part of the scene. We apply it in real time, and it is also agnostic to the viewing hardware. The results of our validation experiments can be seen in the graph. The y-axis account for the user's vote count, while x-axis account for the preference in terms of quality and motion realism for both image and video. We verified that users perceived better quality when our method was applied, while they were not able to distinguish that any manipulation was taking place. Our second application is related to constraints in physical space. Virtual environments are considerably larger than the available real space, which is usually constrained to a standard-sized room. Additionally, most popular consumed VR applications, from video games to training simulators, rely on scenarios that exploit lateral motion with actions like searching or dodging, assuming the user is seated or standing. These lateral translations can be hindered by the physical space, so we propose to use our expansion thresholds to reduce the real necessary space to complete the tasks, again without users noticing it. To do this, we basically expand virtual lateral movements depending on the scene layout, so that a user can complete the same virtual movement in a smaller physical area. Our validation experiments verified that users could actually complete the same virtual task within a smaller space and without perceiving our manipulations. Our final proof of concept application is related to motion sickness. Motion sickness, or cyber sickness, usually happens when some discrepancies between visual and vestibular cues occur. When the camera trajectory is pre-established, there tend to be conflicts between its movement and users' head movements. And then, self-motion illusions, also known as vection, arise. We propose to apply our compression strategy to reduce the compound movement from the camera and the user's head motion, so that vection can be reduced. We validated our technique by measuring users' discomfort, represented in the y-axis, over time, represented in the x-axis. Our results, in yellow, proved our technique slightly reduced compound movement, and therefore, sickness was decreased. Those are three key problems in VR that can leverage our findings in terms of lateral motion manipulation, but as they have been computed in free viewing conditions, their applicability can be expanded to a wide variety of applications. To conclude, we have presented the first work in measuring detection thresholds for lateral motion in free viewing conditions, proving it is possible to unnoticeably manipulate users' lateral motion. We have also analyzed the influence of the scene layout and found an important dependency with the relative depth of the elements of the scene. Our findings are agnostic to the particular VR system used and can be applied to static and dynamic scenes, and can also be safely applied without incurring in performance degradation. We have demonstrated that our thresholds are robust and can be used to address several open problems in VR. We believe our findings will help further understand the relation between real and virtual motion. Remember that our code and data are publicly available. Thank you for watching.